My bad, guys. My bad. So, what is the external? No clue. I will start off just going over some basic stuff. So, solute, solvent, memorize contact process. I believe so, but that's Unit 4, so you'll cover it later. Basically, firstly, solute, solvent, solution. I feel like these can be like really confusing, especially when you don't see it in like a diagram. So, firstly, let me get my pen out. Hopefully, this is writing. It is. Cool. Uh, solute is generally something that we are dissolving in something else. The solvent is what we're dissolving it in. So here we have some solution. We're dissolving a solute in our solvent, and we get some solution, right? It is mixed. In this case, it is mixed. That's kind of it. For what makes a solute and solvent, it can be a lot of things. The solute can be any state of matter. Commonly, you'll actually see, oh, it's some like, I don't know, some solid sodium chloride, right? And you're dissolving it or something. But it really can be anything. Um, so solute could be anything. The solvent is typically a fluid, like a liquid or gas. There are some weird cases where it can be a solid, stuff with like alloys, and it can mix in. It's very rare. I've not seen this. You don't have to worry about it. These two are probably your main scenarios. So just some basic examples. Maybe I have some salt. This is sodium chloride. Dissolving it in water to form a solution of sodium chloride. Maybe we have acetic acid dissolving in water to form a more diluted form. And then we have a gas and another gas to form just some solution, right? Um, Other than that, a solution can either be homogeneous or heterogeneous. A homogeneous is where everything's distributed evenly, so salt and water. So common you'll see in terms of diagrams, you'll see like, let's say I have some solution. Maybe let's say I'm dissolving salt, I'll have my H2O and I'll have Na plus, and it'll be thoroughly dissolved and mixed in to the solution, right? Etc. Whereas heterogeneous, it can be they are not evenly distributed; they are separate. So the most common example that comes to people's mind is oil and water. If you've ever seen it, you'll have some beaker, and you'll see that we have water on the bottom here, and we have oil sitting on top of it. This is to do with densities, and they can't hear. Um, am I not coming through? Is my audio? It is? Okay. Yes, you're tweaking. Is this supposed to be slides? You don't see any. What? Okay. Um, cool. I'm gonna be guess I am good to continue. Okay. Uh, so these will sit on top of each other, right? Um, hello. This to do with densities. Something you may have heard is stuff with like helium. If you think about helium you may have heard, oh, if you put it in a balloon, the balloon will float, the balloon will float, right? And that's to do with helium being less dense. So at first you might think, well, are gaseous solutions always heterogeneous? And it's true that some are lighter or less dense, but it's important to remember that for gases, they will always diffuse into each other, right? Um, and when they diffuse, they will become mixed, right? And the most common example is in our atmosphere. We don't have layers of gases. Our atmosphere is made of lots of different things. Um, and so, is this being recorded? Yeah, it is being recorded. It will be uploaded later. I've also tried to write these slides so that you can actually go through them all fully by yourself. It's written so there's not like some crazy stuff that I'm saying in person that you can't all just read on the slides. So hopefully it should be pretty self-explanatory if you want to just go through yourself later. Yeah. So think about atmosphere. There aren't like layers of gases. Everything's mixing each other. The helium example is because it's typically in some balloon, and then the balloon, it cannot, the gas in here, right? It's not touching the outside. So this is just lighter. Cool. Uh, my existence is redundant. It is redundant, but I'm here to potentially go through it all, answer some questions along the way. So yeah. So the solution type and state of matter, they can be different things. So homogeneous, I'm showing different examples. We have a solid and a liquid, we have a liquid and a liquid, gas and gas and liquid, right? And then for the opposite, we can still have solid and liquid. Again, these can be either one. Liquid and liquid, these can be either one. Gas and gas, either one. Solid and gas, liquid and gas, etc. Right? And an important thing to note is these are homogeneous if and only if they are below the saturation point. What saturation point is saturation point is the point at which when I'm dissolving something into a solution or into a solvent, if let's say I have H2O and I want to put in some sodium chloride. When I'm dissolving something like this, it is below saturation point if it will dissolve. At a certain point, if I put in too much sodium chloride, then if I put in too much sodium chloride, then it will become saturated and I will no longer be able to put in more sodium chloride. It'll hit like a maximum, right? So there's just like a bunch of sodium chloride. Again, when it dissolves, it turns into ion form. That is like from old units, something like that. It is fully saturated. It's not going to dissolve anymore. If I try and put in more, then it will become oversaturated. Cool. That is just like some basic stuff that I wanted to establish. Why is air and atmosphere both? The example that I used was to say that gases will like diffuse into each other, which means they mix thoroughly, right? Um, if you imagine like in atmosphere we have like nitrogen gas and we have like oxygen gas and we have CO2, etc., right? But it's not like if you imagine an atmosphere we have like a layer for each one, right? They are fully mixing each other. But I use the example of a balloon to say that when I have a balloon filled with helium, the helium inside the balloon can't mix with the surrounding air. That's why the helium floats. The helium is less dense. But even though it's less dense, we don't get separated layers of gases. That does not happen. Right? Cool. Aside from that, we can actually start with the main chunk of Unit 3, which is reversible reactions. So, what is a reversible reaction? We have some, I don't know, some reactants, some products, right? In our normal, whenever you're reacting, you'll typically like CH4 plus blah 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 forms this, and you'll see this arrow here. What this tells you is that this reaction is not reversible. It can only happen in one direction, right? This can only form into this, and it can't go the other way around, right? So the most common example would be stuff like combustion. If you try and do combustion, so you get CO2 plus H2O. If you look at a combustion reaction, it is only one way. We cannot take this CO2 and H2O and turn it back, right? That is a reaction that is not reversible, right? So what we want to do is we have a reversible reaction. What this means is these reactants can turn into the products, and these products can turn into the reactants, right? Also, if you guys do have questions, do ping my alt. I think I said it in the chat. Um, the my alt, I will type it again just in case if anyone else has joined. Ping that because I will see that on the side. Yeah, so you didn't have a question, so I don't know why you just. Yep, no, thanks guys. That's not those aren't questions. um. Anyway, um, this can go both ways, right? So we have what is the forward reaction that can occur, and we have the reverse reaction can occur, right? uh, both reactions can occur, and if it is at, we'll cover it in a sec, but just a short summary, if we have what's called at equilibrium, then the rate of this forward reaction and the rate of this reverse reaction are actually equal to each other. So let's just look at a reversible reaction. We have some reactant. This is the number of molecules. In this case, I've chosen nitrogen dioxide. We're going to see this example a lot. I'm going to use it later on. But anyway, we have some product, and then I guess this is a 1 here. And the most important thing is to signify a reversible reaction, we must put a reversible arrow here. It just looks like that. That's all you need to know. Hopefully that's fine for now. Cool. So let's look at this. A reversible reaction, we have NO2 becomes N2O4. So that is 2 molecules of nitrogen dioxide become 1 molecule of dinitrogen tetroxide. But the important thing is not all the NO2 becomes N2O4. So in a closed system, we're going to have some of this, some of this. So if you look at a diagram, maybe we have like NO2, 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 and then maybe we have some N2O4, N2O4. We have both. And they're just chilling with each other. There is a reaction that's constantly happening, and that is called, and at a state of equilibrium, called dynamic equilibrium, right? And why do we call it dynamic? So, firstly, rate of reaction. It's the rate at which the chemical reaction will take place. That is unit 1 and 2. Why is it dynamic? Because in our little box here, we have the NO2 molecules reacting with each other to produce N2O4. But we also have the N2O4 molecules breaking apart into NO2. And this is happening, it is constantly occurring, and it's non-zero. This is constantly happening, so it's non-zero. And both rates are equal to each other, right? So think about it this way. If, let's say every second, 2 NO2 becomes 1 N2O4. This is the forward reaction, right? But the reverse reaction is also happening. So we also say every second, and my handwriting's a little bit bad, every second N2O4 becomes 2 NO2. Hopefully you can see that with these two being equal to each other, at equilibrium, which is dynamic equilibrium, it is dynamic because it's constantly changing, but the actual concentrations of each, they don't change, right? Concentration of the reaction product with dynamic equilibrium is reached is the position of equilibrium. So this is just the point, right? At this, let's say at this instant, the concentrations aren't changing. This is the position of equilibrium. Hopefully that makes sense. Cool. So reversible reactions. A reaction is reversible reactions, and we're looking at forward and versus endothermic. Exo versus endothermic. In this case, I'm going to tell you that this reaction here, has a delta H of negative 58 kilojoules, right? So this is an exothermic reaction. It is releasing heat, right? So here, the reactants start with this much energy. This is energy, and this is like, I don't know, reaction progress, I guess. So reaction progress. So as it continues, this amount here, this is called the activation energy. Activation energy, hopefully you're familiar with that as well. And this amount is our delta H value, right? So if our reactants start with this much energy, they require this activation energy, and they will come to our products. These have less energy, so this releases heat, right? Now, the important thing is that for a reversible reaction, remember our products for the forward reaction are the reactants for the reverse reaction. So these two are the same thing. Notice they're actually at the same height, right? I think this diagram is actually a little cool. I think they're like slightly off. You know what? Pretend they're the same height. These two are the same height. So these reactants have the same energy as these products. So to go back, these products have the same energy as these reactants, right? What that means is, if my forward reaction is exothermic, which it is in this case, then my reverse reaction should be endothermic, right? If this one releases energy to get from reactants to products, this one must take in energy to get from what was the products to now the reactants. Does that make sense? Hopefully it does. With that, we're going to go on to equilibrium constants. So here we have I don't know, just some generic equation. We have some alpha times some molecule A, beta times some molecule B, gamma times some molecule D, delta times some molecule D, right? This is us trying to quantify the position of equilibrium, right? We have some concentration of all our reactants and products, and they're in some box or whatever, in a beaker, who knows? But we want to actually quantify what is this point, right? So we will write it in this form here. I think this is on your formula sheet as well, so if you forget it, you don't have to memorize it. But the equilibrium constant is this one of our products to the power of the thing in front of it times the other product to the power of the thing in front of it. And maybe if we have plus, let's say, I don't know, pi E, for example, then I would just chuck another one, concentration of E to the power of pi, right? That is just us. It is just the product of all of these to the power of their coefficient, right? Cool. And we're going to do the same thing for the reactants. It is divided by the concentration of our first reactant to the power of that, of the coefficient, multiplied by the concentration of second reactant to the power of the coefficient, and that's it, right? This is our Kc expression. So Kc being the equilibrium constant, right? If a chemical in our reaction is a solvent, we do not include it in the equilibrium expression. So here's just an example. Here we have acetic acid or ethanoic acid plus water. It will dissociate into an ethanoate ion and a hydronium ion, right? This is a reversible reaction, you can see from the arrow, right? And the Kc expression is this to the power of 1, because there's a 1 in front, this H3O plus to the power of 1, because there's a 1 in front, and divided by CH3COH, which is acetic acid. Notice I did not write the concentration of H2O, because H2O is a solvent, right? In this case, H2O is a solvent, so it is not participating in the reaction, and we just leave it like this, right? For completeness, I will say that generally I've been taught or I've seen that we say Kc is unitless, right? It has no units. Some sources actually tell you that it has units depending on the equation. So let's take this example, right? I know that all of these are concentrations, and I measure concentration, let's say some concentration of something, it'll be something in like molars, which is moles per liter, right? So if you look at the units, we're purely doing maths off of units right now. We have m times m divided by m. So these cancel, and we have m. So the units of this Kc expression would just be molars, right? But in a case like this, it'd be more complicated, and maybe there's some more examples. Generally, I've seen people just take it as unitless. Some sources say this. There's not too much I can really say about it. I've seen both, right? I think that's you only include gaseous and aqueous. Uh, yeah. I guess I should say that in this. That's a good point. You don't include solids either. No solids either. The reason being, I guess I probably should have said that's my bad. If I had, let's say, copper metal, right? I can't take the concentration of a solid. That's not something you can do. You can mark down for keeping it unitless all the time. I kept it unitless all the time. H doesn't react. Is it H plus, or is that dissociation possible without H2O? That's a good question. In this case, the isn't there a description regarding this QCAA paper? I'm not 100% what you mean. You're gonna have to show me the example. But back to the other one. For this, the reason we say we don't count the H2O here is if you look at this expression, the H2O is purely enabling this to split. This is an ionic compound, and this is a polyatomic ion, right? CH3CO minus is an acetate ion, ethanoate ion. It is purely there for that, right? So the only purpose of the H2O is to help it split. you can also rewrite it because you're saying, oh, doesn't it contribute? You'll also see that people write H plus instead of H3O plus. Is there any way I can add a page? No, I don't think so. It's okay. You also see people writing that. So like a equal alternate expression would be to say CH3 COOH reacts form CH3 COO minus plus H plus, right? So this is aqueous. Oops. Aqueous, aqueous, aqueous. In this case, there is no H2O, right? Add a new slide in PowerPoint. Can I do it while I'm presenting? I don't think I can. At least I'm trying and it's not working. I don't know. It's okay. So yeah, the H2O here doesn't actually count. In fact, H2O, all it does is it's acting as a polar solvent. Something you know is like dissolves like. Dissolves like. It's really important. In this case, H2O only acts as a polar solvent. You could choose any other polar solvent, and the same thing would happen. That's really the only purpose of the H2O. It doesn't participate in this bit, right? So yeah. What's the other thing? What if the superfine particles of a solid suspended in a solvent or reactant? Superfine particles of a solid. Is that considered aqueous? For it to be aqueous, aqueous obviously being dissolved in water. An important thing is we have H2O like this. We have lone pairs here. The reason why, let's say, sodium chloride is aqueous in water is because there is a polar bond between the negative charge here, because these are lone pairs of electrons, it's very negative, and the chlorine, which is, sorry, the sodium, Na+, which is very positive. So there is a bond here, right? Superfine particles of a solid being suspended, unless they are being like literally attracted to the water molecules, I would say that no, it's not aqueous because it's not actually dissolved in the solution. Right? Hopefully that makes sense. They are. It's like I'm saying in my head. I'm thinking like dust, right? Unless it's being attracted in this form, we can't say it's aqueous because it's not evenly distributed. Maybe it's like floating on the top or something. Question makes in files as well. When water is one of the reactants, we don't include. When water is wait, water's on the reactants. Um, I'm not 100% what you mean, Johannesburg, but if I just have in a combustion reaction, for example, when I produce, there's some space here. In a combustion reaction, I will produce some water vapor. In this case, I will consider it, right? It is a gas here. I do consider the concentration here. I guess this isn't reversible anyway, so you can't actually have a KC. It's not even reversible. Let's just say pretend we had some reaction, produce H2O. I would consider this. If H2O is a reactant and it produced some stuff, then yes, I would consider it was a reactant. It actually reacted. Then yeah, I would consider it in the KC expression. KC change with temp change, but not with pressure changes. I think I will get to that. They included water. Let's see. Yeah, you include so for the example that some just sent in the chat. I guess he did just send it, but it was a while back. That's a really good example. Water there isn't being a solvent. If you look at the left hand side, it's alcohol plus carboxylic acid. It is producing water, right? It's not being used to dissolve something or anything like that. It is being used as part of the reaction. Yeah. So yeah, it's not being used to dissolve anything. It is there. It is water. It is liquid, but it is being produced, and so we do consider it in that scenario. Hopefully I got everything. I will continue. Someone just like does H2O not actually react in the dissociation of acid or base? What actually occurs there? What is associating a thing that exists? Oh, there was a special name for it. I wish I remembered it. But in a water molecule, right? We're gonna go back to this. When we have, let's say, HCl, and I'm dissolving HCl in water, right? I will get H plus and Cl minus, right? Let's actually think about what this H plus is. this H plus is a hydrogen atom. So a regular hydrogen atom is just a proton in the center with an electron surrounding it, right? That is our basic hydrogen atom. What about the hydrogen ion? Well, it's the same thing, but we don't have an electron, right? And so in this case, we want the hydrogen ion to it wants to get a full shell, right? That's the objective of all of chemistry is atoms want a full shell, right? So it thinks, how can I go from having nothing to two electrons here, right? And there's a special name, maybe Panda will know, but what actually happens is sometimes you'll see H plus, sometimes you H3O plus. The reason is a what happens is H2O, we have OH, H. Our little H plus ion will form a bond here. It'll do this. It'll steal these electrons, this lone pair, and it will just form a bond, just right here. It'll just take these two. It didn't have anything to share. Normally in covalent bonds, you'll see they share. It just takes it, right? Um, so in a way, it is a like a polar force of attraction between these two. It's not even a new molecule in itself. I think the name is. Don't quote me on it. I think the name is a dative covalent bond, but someone can double check me on that. I'm not 100% myself. That's not syllabus. You don't need to know this, but just to answer that question, um, it doesn't react. It just sits there and looks pretty. But then the H plus comes along and is like, "Oh, I'm gonna stay attracted to you right there," and that's all it does. Um, can you get H4O2 plus, where two protons H, so like something like this? Um, it's a good question. I would have to look it up. My gut says it's too unstable to exist, but I genuinely don't know the answer. You can have a look and see what Google says, but my gut says that it's too unstable. But you can maybe I don't know. Yeah, cool. What about KC? So the KC for any reaction equation is always the same, as long as the reaction temperature is the same, right? This is a very, very important thing. As for a Y, I wish I could give you. Google says unstable. Okay, Vesper theory, that could be true too. So yeah, so KC is always the same no matter what for a given temperature. For a reason why that's true, I actually couldn't give you. I wish I could give a Y for everything in chemistry, but unfortunately, it doesn't end up like that. For now, just take it as is. Unfortunately, the KC at any one temperature is fixed, no matter what other conditions I change. If I increase concentration, or if I increase pressure, or whatever else. But as soon as I change the temperature, the KC for a molecule or for a reaction, sorry, will change. Um, yep. So yeah, if temperature of reaction changes, the KC changes too. And we're going to look at this a little bit later. Okay. So let's actually do some calculations. What is the KC of our reaction here? So firstly, let's figure out what our expression is. We know that Kc equals the concentration of N2O4 over the oh, you guys didn't see that. Concentration of NO2 squared. So hopefully that makes some sense. Let me get a highlighter up. NO2 is come down here. Can I switch colors, or is that? Yes, I can. N2O4, that is our products, is come up here. And let's get a blue. This 2 has come over here. Hopefully you guys can see where all of that was. It was the wind. It was the wind. So then we can just sub it in. We get 0.5 over 2. Oops, let's write a bit closer. 0.5, that is concentration of N2O4, over concentration of NO2 is 2 squared, is 0.5. 0.5 on 4 is 1 on 8, which is 0.125. If you're curious for the actual value of Kc for this reaction, it is not this at room temperature. I just chose this because it's a nice number, it gives an easy example for us. Yeah, it is the brown Panda. It is the brown colorless, and the fact that it is I'm using that fact later on. We'll come to it. We'll come to it. We'll come to amphiproduct later. I haven't been reading the chat fully. So this is just the answers. That's it. Okay. Amphoteric versus amphiprotic. I have not heard those words. Some. Panda says no. So, going on to Le Chatelier's principle. Maybe you've heard of it. Le Chatelier's principle is all about what if I have something at equilibrium and I change it. I'm like, I will add some chemical, or I'll change the pressure, or I'll do something, right? And what happens? So I don't know. You can Le Chatelier's, LCP, Le Chatelier's, just like that. All of those are the same. Ella, I don't think so. I'm pretty sure those are different words. I just forgot it. Amphiprotic is its own thing, but amphoteric I've heard. I don't know about amphiprotic. Yeah, I think you guys are answering. Cool. Personally, I'm a fan of LCP. It's very, very short, very quick, and it's completely fine. So, what is LCP? So, LCP just tells us that if we if we do some change, then the system at equilibrium will do whatever it can. Do external markers accept LCP? I'd hope so, because I wrote down LCP. So yeah. Um, so LCP, what it does is if we do some change, it will do whatever it can to oppose that change, right? So let's say I added some more reactants, then it'll do whatever it can to decrease whatever I added. If I lower the temperature, it will try and increase the temperature. If I increase the pressure, it'll lower the pressure, right? It works really. That's just kind of it. It will do whatever it can. um, it'll do whatever it can to oppose whatever our changes, right? Um, and so we're gonna go through some examples, right? Uh, should we write according to LCP in every question, or is it inferred? I'm not gonna lie. I couldn't give you a guaranteed answer, but personally, I would. Yeah, depends on marks given is good. I would say write it though. I think it's definitely doable. Like it's not taking too much extra time, and I think it's not worth the risk. Chemistry marking scheme can be very dodgy, and sometimes it is, sometimes it's not needed. Do arrows explain flowcharts? My teacher said no. I'm not sure what you mean. I differentiate exo and endothermic reaction for the forward based on different wording. Could you explain what you meant by that? I didn't fully get it, unless someone else got it and could explain. Can I mark your Chem EA? I would fail you. You specifically though, no one else. Can we use LCP to explain Lenz's law? No. Yeah. So, let's go to LCP. These are the main things you'll see. If there is a change in concentration of at least one of the molecules, so maybe I added some reactant product, or I can cause I diluted it, then this can cause a change in partial pressure. If you haven't heard the term partial pressure before, I will cover this. We will cover that on the next slide. You might have just heard pressure, but I want to really get clear. There is a difference between pressure and partial pressure, and we'll cover that. So there's that, and last one is a change in temperature, and it will try and oppose that. Let's go through these just one by one. What is partial pressure? So partial pressure is the pressure that a single gas in a mixture would exert if it occupied the entire volume of on its own. So imagine I had some box here, and in this box there was N2 and H2 and O2 and whatever else, right? And there was some mix of them. If I wanted to look at the partial pressure of partially the same as concentration for gases, yeah, in a way. I know it's not the exact same, but I think you can think about it similarly. Trust Panda though. We're getting to partial pressure. Trust. So let's say I have this closed container, and I've got all these gases in, right? And it's a mix of them, and they're all jumbled up, right? If I have a mix, the partial pressure of N2 is, imagine I just deleted these. These guys are gone, right? And all my box had is the N2 that it was originally, right? This is what I look at when I talk about partial pressure, right? I'm only looking at this N2. I'm not considering the space that's taken up by these gases, right? And that's really important because if you remember the ideal gas law, we said very specifically that um, I don't know, I can't be able to read all that. Um, in the ideal gas law, we said they don't interact with each other, they don't take up space, they don't have size. That was, if you don't remember, ideal gas law was PV equals nRT, right? If we're going to talk about pressure, we really just have to think about, well, the partial pressure of N2 is if it was just N2. H2 and O2 are insignificant. They don't take up space, they don't exist, they're just there, in theory, right? The partial pressure is just for this N2. And that's really important. That's a really important distinction, right? And let's think about why. So, um, if I just had N2, let's say, yeah, according to this, each gas fills the volume of the container completely in. So let's say I added a new gas. So I added some CO2, right? Some CO2 got added to this container. If I added CO2, the partial pressure of N2 would not change, right? Um, yeah. The partial pressure of N2 would not change. It would stay the same because we are ignoring this addition of CO2. Does that make sense? Yeah. You might have heard it with different words or maybe like phrased differently. Do we really need to know this? Well, the biggest thing is I want to point out the fact that this CO2 being added, this is something that a lot of people get wrong. People think, oh, well, if I add a gas to this container, then the pressure inside the container increases. And so, blah, 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 we know that LCP is caused by pressure change. That's not exactly true. The pressure change is only true for the molecule itself. If N2's partial pressure changed, right? Adding more gases that are a different type does not affect the partial pressure, and it does not. Yeah, it is PV equals. You don't need to know this. That was just this is the assumptions, right? Explain partial pressure. Why doesn't it though? Good question. It does. It does. It yes, there is less space. But when we're doing chem, we think, oh, this is I don't know. We don't want it to be realistic. So we just lie. We lie. That's what we do. That's what we do in chemistry. And as good liars, yeah, basically, yeah. As good liars, we make assumptions, and that assumption, this is our key assumption, that we assume it doesn't take up space, it doesn't do anything, right? Realistically, it does change stuff. That is important. It will change stuff. Yeah, it can include assumed knowledge. Yeah. um, but yeah, it will. It does take up space, but in theory, we don't consider that. So, with that being said, some questions. Do you think if I had a closed container with NO2 gas, right? Which of these do you think would affect the partial pressure of NO2 gas? I don't know how you guys are going to answer. Just give me like, I guess, a sequence of yeses or nos or something. Don't understand. While I get hopefully some yeses and nos, um, no, yes, maybe. So, um, interesting questions. So, first one, adding NO2. This one will change the partial pressure because let's say I have some closed container, right? If I had 10 moles, I don't know, 10 moles in like 1 liter of volume, if I add more NO2, then that is directly just changing this, right? And if I'm just adding NO2, then this number goes up to like 20 maybe. So now the pressure is a lot more. I have more of these molecules in the space, so the pressure's higher, right? Uh, Adding H2 and unreactive gas, it is not. If I had 10 moles again, then if I add some other gas, we don't actually care about it, right? It is not affecting this because we only look at NO2 here. Increasing, decreasing volume of container, absolutely. This is 2 liters, 3 liters, I don't know, 0.5 liters. These will change the volume, and so the pressure will change as well. Concentration of gases. Yeah, it's very similar to concentration of gases. Is just the surface of the container is reacting with the gas? So the last one I want to get is the surface area. Keeping the volume the same it's a little bit tricky, but if I have some container, like an MCQ, this explaining or MCQ on partial pressure is highly unlikely. It's more likely to be like if it was going to be something, it'd be like which of these affect equilibrium or something, right? And all I want to get out of this is which of these affect the volume, or which of these affect equilibrium. And all I want to get out of that is if they had an answer that was like adding H2, for example, you know that H2, in terms of the gases, it will take up, or like it should take up space, but we do not say it affects equilibrium, right? Yeah, and you can cut up the same cube. What time am I expecting to finish? That's a great question. It's already going way longer than I thought. So, oh well. Yep. Hopefully we can get through it pretty quickly. I'll try and speed up a bit. So yeah. Would this be an MCQ? Because if it's short answer, it doesn't matter. And surely we wouldn't look at responses to explain or stuff. That's what I was saying. That the question, an MCQ on partial pressure is unlikely. It would be something about LCP or would it affect equilibrium? And all I want to get out of this is, that certain things will change the pressure, right? And I just want to make sure we're clear on which thing can affect equilibrium, which things can't. Wouldn't look at responses to explain. I'm not 100% what you meant by that. No, you're good. Yeah, ping on the other account. Um, it's because I have my other account on the side, so I can see the little yellow highlight when you're pinging me. No. You're good. You're good. Okay. I was just saying for this last one, keeping the volume the same. Pressure is directly to do with the volume. It's not to do with the surface area. That's kind of it. It's just how much space. If it's taking up 1 liter of space, it's hitting all these sides, right? And it's the pressure is to do with how well it can fill the space. If we change the shape of the space, it doesn't matter. It's just how well it can fill that space. Hopefully that answers that. We can move on. Keep asking questions, and then I'll come back to it if I need to. So, I think we'll have some practice questions, and I'll come back and answer anything I missed later. Temperature. So we know that if I have a reversible reaction, one of them must be exothermic, the other one must be endothermic, even if they're slightly exo and slightly endo. Did I miss anything you joined late? The slides will be posted later, so you can catch up if you need to. This is fairly simple. If the temperature is increased, right, the position of equilibrium, or the equilibrium, it wants to shift so that we will decrease temperature again, right? So if temperature is increased, we want to try and take in energy out of the surroundings to lower the temperature. Whereas the slides, I will post them. I haven't posted them yet. Yeah. So, position of equilibrium will shift to absorb energy from surroundings. Hopefully you know that to absorb energy from surroundings, that is the endothermic reaction. So, if I switch to my highlighter, yep. If temperature is increased, endothermic reaction is favored. If temperature is decreased, exothermic reaction is favored. Hopefully that just makes sense. If I lower the temperature, I want to do something to increase the temperature, and so the exothermic will release heat. Is in a beaker and there's hot water on the outside. Which way would it be favored? Um, so for the first one, if there's hot water on the outside, then I mean, if you think about like ice baths, right, where we have if I switch back to my pen, we might have some beaker and we place it in a tub of cold water or something. I don't know, right? The point of that is to cool down this. So if you put it in hot water, then we are effectively increasing the temperature. It will favor the endothermic reaction. It'll take in the heat. Yep. What was the scenario? So if surface area of a container was changed, if the volume stays the same, um, the easiest example I could think of is I'm doing in a 3D case. Oh, not 3D. I'm doing in a 2D case. Um, so in a 2D case, imagine I had a box, and this is a cross section or something, right? So let's say this is a 4x4 box. The area of this box area is 16, and the surface area is what? 8 plus 8 is also 16, right? If you look at this one, so I'll say volume, even though I know it's the area. Let's say area and perimeter. That's a much better one. If I had a something like this is a 1x16 box. The area of this is still 16, but the perimeter is now what 30, 34. So this is similar concept where if I had a 3D case, we could have two things with the same volume but a different surface area as in the different perimeter. Hopefully that makes sense. It's not something, it was just an example. You didn't have to like come up with different box shapes or anything. So we want to maintain its own equilibrium with the surrounding. Um, it will respond to a change in its temperature. If its surroundings change temperature, then it itself will change temperature. Like if I had a like a something like a beaker or something under a Bunsen burner, then yes, this is the hot thing, but the hot thing is heating up this thing. You know what I mean? Yeah. Cool. I will move on. So, um, here is a question. I want you guys to have a go at this. You don't have to type it up. Maybe you can just have a think about it. I'm not expecting typed answers. I do have a typed answer on the next slide that I'm just going to go through. But we have our classic case again. I have nitrogen dioxide, and I'm telling you, nitrogen dioxide is reddish brown, and dinitrogen tetroxide is colorless. Right? You don't have to. That's just something you can. I've just told you. It reaches equilibrium in a transparent closed container. I've said transparent so you can see the colors. That is useful. I'm going to shrink the box, right? This will reduce the total volume. And I want you guys to tell me how you think the gases inside the box will change. And when you are typing up your answers or when you're like writing on an exam, these are the kind of things you should be considering and explaining in your answer. I'll give you guys a little bit to have a little think. I will go over to the next slide. It is being recorded, don't worry. He is recording it as well. Oh, tomorrow's one? Sorry, my bad. Give it a little bit longer. I'm concerned about finishing in time. Oh no, I mean I don't really have a time limit. I guess I do. Oh well, it is gonna go for a while. That's my bad, guys. So I think I will move on. Hopefully you guys had a little bit of a think. So this is, I've just written it in full. Oops, what just happened? My bad, guys. Box is shrunk, volume will decrease. If volume decreases, the pressure will increase. Also increases concentration of both. I guess it's not really needed because if both are true, then if both increase, then there's no difference, right? But the pressure will increase, which is important because the equilibrium wants to shift to favor the side with less particles. If the pressure is higher, then I want to get less, right? Yep. Position of equilibrium will shift to the right. Why? There's two particles here, one particle here. So, two particles on one side, one particle on the other. Forward reaction is favored, right? Concentration of NO2 will be reduced because we said the forward reaction is favored. Concentration of N2O4 will increase, and then we already said the colors, and so it will change to a lighter shade of reddish brown. Cool. Well, yes. What Panda said. That is very good. All the gases will take up the same amount of space. So even though this might be a bigger molecule itself, we say it in terms of we're considering them like a dot, right? They are taking up two molecules is bigger than one. Cool. I did have some other questions. If you guys want a screenshot, and then maybe you can think about what you would put for answers, and maybe you can send it to me. I'm fine with that. Any tips to hit mark allocated for these types of questions? Done range from 3 to 4. That's a good one. Remind me about that later. I think it's a bit of a long answer, so or maybe Panda can answer. Panda can hopefully get to that. So yeah. So yeah, there are some questions here. You don't have to do this now. You can think about this later. I will move on for now. There are answers on the next slide. Cool. So this equilibrium stuff that we were talking about, this is not just for I don't know, those weird equilibrium reactions. We can do it for acids as well. So acids what's happened? My bad, guys. Acids donate H plus in water. These are areneous acids, but we'll learn another type later. Not all acids want to fully donate everything, right? Some acids will keep a bit. These are weak acids, and they will partially dissociate. Acids that release all of them are called strong acids. That is our difference. So HCl reacts with H2O. It will fully release everything. We say here you have a little forward arrow, right? It's one way. Whereas we have ethanoic acid, it is reversible. It only releases some of it, and some of it stays on this in the first phase. There's a mix of both, right? Yeah. So when we say strong, it's more of the chemist propaganda. They've been lying to you. Yeah. We say it's forward. It is actually like it's partially reversible. Like there's a tiny bit that can be reversed, but we generally say it is almost fully here. Technically, that you're right. Some can stay like that, but it's such a small amount that we consider it like negligible. Cool. Strong acids, some of the ones you got to memorize: hydrochloric, nitric, and sulfuric. Some categories: an acid is monoprotic if it can only donate one H plus ion. It is diproduct if it can donate two, and it is triproduct if it can donate three. Hopefully, you see the prefixes: mono, di, tri, right? And lastly, polyprotic. It can donate at least two, right? So if we look at our categories, this one is monoprotic. I'll just write mono. This is mono. This is di, and it's also poly. Hopefully that makes sense. Going through these fairly quickly. You guys can talk about whatever in the chat. I don't really mind. But if you have any questions, do ping me. What about amphiprotic? We will cover amphiprotic species. They are coming up. It's not a specific type of. Yeah, we will get to them. We'll get to them. Don't worry. Just like acids, we can do the same thing for bases. So bases can be strong or weak. And I'm also going to cover Bronsted-Lowry bases too. So Arrhenius bases, this is the same, like the first thing you might have heard, is Arrhenius bases donate OH minus ions in aqueous solutions, right? But a Bronzolari base is a little bit broader. Bronzolari base or Bronzolari acid just donates a proton. Remember, a proton is also a H plus ion. And a Bronzolari base is anything that can receive a proton, so it can just accept a proton, accept H plus. Who's gonna? So yeah, cool. And the reason I mention these together is because most weak bases are Bronzolari bases, right? Um, these are just some examples. These are I've just sort of this first table. You don't have to memorize these, right? These are just some examples. These ones you should know, I think. Um, I think these are probably I think these are probably a lot more important to know. Ones you should memorize are below. These are just some examples, and I separated them into the categories so you can just see the difference, right? So, for example, these ones have an OH minus ion, right? A hydroxide ion. They can release this. Barium hydroxide. Oh, it should. That is my bad. There should be a 2 there. Thank you, thank you. Yep. So it could be like this, and then Bronzolari, you can see these donate H. These can accept a H, right? But these ones can't donate an OH minus. There's no OH minus for these guys to donate, but they can still accept a H plus, right? Cool. The reason this is not an Arrhenius one is because this is ammonium, I believe. Ammonium is the name. It is gaseous, whereas Arrhenius we were looking at just in water. This can donate, but it is a gas. Cool. Um, cool. Again, if there's any questions, do ping my alt. Okay, moving on. Amphiprotic species. I saw someone talking about this in the chat. An amphiprotic species can act as both a Bronzolari acid and a Bronzolari base. It can do both. So one of the ones you need to know is water. Water, you have to know, is an amphiprotic species. Here, water is acting as a base because it will accept a H plus ion. However, in this case, water is acting as an acid and it will donate its H plus ion, right? Um, yeah. Another example, common example, is HSO4 minus. That is, yeah, molecules base, molecules acid. It can work both ways, right? So it can produce sulfuric acid or it can produce a sulfate ion. Arrhenius, it's a scientist. That's just the guy's name. I'm pretty sure. Nothing special about him. Yeah, he's the guy that similar to if you're studying physics, you might know like the different models of the atom. We have like Dalton, Bohr, etc. Arrhenius is just the guy that first came up with the theory of acidic versus basic, and Arrhenius said that an acid is something that donates H plus in water, a base is something that donates OH minus in water. But then we've kind of evolved the definition over time because we've gotten more like precise. Blood buffer. Yeah, we will cover buffers and blood specifically later. Um, I'm not sure if it's amphiphotic. I don't know what that word means. Um, cool. Conjugate acids and bases. This is another thing you need to know. If I switch my pen color, ink color to, let's say, green. Cool. So all you need to know is if I have, I think I missed something, but looks like Panda got it. HCl, it is a strong acid. That is something I said you need to know. It can lose a H plus, or it acts as an acid and it will lose a H plus and it will form Cl minus, right? These are conjugate acids and bases. They differ by one H plus, right? So this is HCl, this is Cl minus. They differ by a H plus, and they are pairs in a sense, right? If something is a strong acid, its conjugate is a weak base, right? So its conjugate is the exact opposite. So if something is strong, then the conjugate is weak. If something is an acid, the conjugate is a base. Same thing here, but the other way around. Oh, sorry, this is a typo. Not a typo. I just miswrote. This should be a base. Sorry. H2O here is acting as a weak base because it is accepting the H plus ion. And then it's gaining the H plus, and it's becoming H3O plus, which is a strong conjugate acid because this is a weak base, strong conjugate acid. Hopefully that makes sense. Also, again, there's sorting through everything in the chat. Here, so this is a forward arrow, and it's just one way because this is a strong acid, so it fully dissociates approximately. Cool. This is kind of a bit further, but remember that old table that I showed you earlier? This is an updated version with all of the conjugates as well. So it's all the base stuff and all the conjugates. If you want to screenshot it, I guess you can. It'll be on the slides, but you don't have to memorize all of these. Memorizing the one I showed earlier, and then just remembering, oh, the conjugate is also the opposite. Cool. And there will be a uniform masterclass, by the way. That'll happen tomorrow. Okay. Still on this, we have buffer solutions. So for a buffer solution, remember we say that pH is negative log H plus. So buffer solutions are used to minimize pH. And so to minimize a change in pH, we want to minimize a change in the concentration of H plus, right? And they work by doing this. So here I have acetic acid plus water, produces this and this. What we'll do is we'll take this, we'll have a massive we have a lot of this, right? But we're also going to have a lot of this. There's going to be a lot of this too, right? Then what do you think will happen? There's going to be a lot, but these are equal, by the way. That's important. A lot, but equal. And just something that you can guys think about. We're about to see it. But in this case, in the example I just said, what will happen if I add some H plus ion or H0 plus? And what will happen if I add OH minus? I'll give you guys a second to think about that. What do you guys, what do you guys think will happen if I add each of these to this solution when I have a massive amount of this and a massive amount of this when they're equal? Just have a little think. Yeah, so I'm seeing a lot of answers in the chat. If I added H3O plus, then equilibrium would be disturbed. It would pose the chain, favor reverse reaction, decrease H3O plus, right? So the concentration of this would go down again because I'm favoring the reverse reaction, right? Yeah. Something else that's important for a buffer system is because these are really large, that if I added a little bit of this, right? We got it right. If I added just a little bit of H0 plus, then these concentrations don't really change. They're massive, and they only change by a bit, right? So they remain roughly equal. They're not equal. That is important. They're not equal, but they roughly change a little bit, right? And for the other one, this is if I added OH minus, exact same thing. Remember, in this case, there's no OH minus, so the change is not directly like noticeable. I can say buffer means resist pH. Yeah, basically. So if I add OH minus, remember that OH minus will neutralize the H3O plus, so it'll bring this down, right? We're neutralizing it, so it's getting rid of it. H3O plus, there's actually also more water. We're reducing water here. That's, I guess, another bonus. H3O plus concentration decreases. Yeah. This exact phenomenon. We're going to see titration in a sec. H3O plus concentration decreases. Number of molecules of water will increase. Equilibrium will be disturbed. Opposed chain favor the forward reaction, because if this is going down, then I want to produce more of it. And exact same final line, because the concentrations of these two are really massive. They barely change. They do change, but they barely change, and we will mitigate the change to H3O plus. Hopefully that all makes sense to you guys. So what? I don't know. Just same thing. Just a quick mini summary. Using the power of LCP, if a solution ever gets or loses too much H plus, we can just mitigate that change by making the disturbance as little as possible, right? And a very common one that you'll see is in our blood. So in our blood, we have a buffer solution, and our pH in our blood has to be really tight. It's to be 7.35 to 7.45, and there are some major health concerns if we have something outside of that, right? That can happen, and that is a serious health concern, can be hospitalized, blah, blah, blah. But it's really important that we keep our blood to that. It's really important that we keep our blood to that range, right? So inside our body, we have a buffer system. It'll keep it to that range. That's just kind of it. Cool. How do you make a buffer? This is something. Do amino acids have to do with blood buffer solution? Great question. Ask Panda. I don't know. How do I make a buffer solution? You might not need this. No, we already talked about death. LCP works with buffers. Yeah. So for this example, with this, we talked about. I'll go to this example. This example is a bit nicer. This and what a buffer is if I add a change, if there's a change in like concentration of H plus or something, what'll happen, right? Yeah, you are. If you have a change of concentration of H3O plus, let's say I'm adding this, right? This should change the pH. That's what we think. It should change the pH. But we have LCP. So what LCP will do is, if the concentration of this goes up, then according to LCP, it wants to do something to oppose the change, right? It wants to oppose the change, and so to oppose a change, we will favor the reverse reaction. Mars, we're still on topic 1 as well. I haven't even reached electrochemical cells yet. This is going to be rough. But anyway, if we increase the concentration of H3O plus, we will end up favoring the reverse reaction. Yeah, we haven't started redox. And so this is a factor of LCP. LCP says, oh, well, if we increase the concentration of this, we're going to favor the reverse reaction. And so it will decrease. And that way, when we decrease this again, according to LCP, we can minimize this change as much as possible. Hopefully that hopefully that makes sense. Yep. How do we make a buffer? You guys might not need this. I got taught it in mine. So yeah. But I will quickly mention it. You have it here if you ever want to relook at it. Is redox the next topic? Yeah, redox is topic 2. External exam begins. Skip it. I want to cover the first bit. I will mention it later. One way to make it is I start with a large quantity of some weak acid or base. Then I neutralize half of it. Don't skip redox. Oh wait, did you mean skip this slide or skip redox? I'm guessing I don't know what you meant. So if I have weak acid or base, I want to neutralize half of it. Then if I add 2 moles of this, I will add 1 mole of a base, a strong base. And if I do that, then I'll get exactly 1 mole of this and 1 mole of this. Yeah. No, I want to explain this slide, this one at least. There's another way with salt. You can have a read of that. I'm not going to cover it. But yeah. Cool. So, more on equilibrium constants. So we have, I guess we'll go through one by one. Just like we had Kc for equilibrium reaction, in a gradient buffer solution, you technically have, and that's why I covered it. So Ka is, if we have an equilibrium constant, but it's specifically for an acid, we'll represent it by Ka. That's what we do. Kc. KC is the equilibrium constant. What does large concentration conjugate acid and base matter to the mechanism? Large concentration just means that the change, when we do LCP, obviously the concentration will change, but because we have so much of it, it barely changes. Like it only changed by a little bit, right? Yeah. So, if we have the Ka or the Kc expression for an acid, we'll represent it by Ka, and for acetic acid, we have it right here. This is the same thing as earlier, but for this specifically. Then shock, we can do the same thing for bases. So here we have CH3CO minus. This is the conjugate base. Oh, this is the conjugate base for our acid on the last. Why can I not rub this out anymore? What's just happened? Okay, well, my thing is tweaking a little bit. There we go. No, you know what? It's okay. So, ethanoate ions is the conjugate base of acetic acid. And here we have the same reaction. It is a base. This is the Kb for our base, right? Hopefully that makes sense. Moving on. Are the annotations still on screen for you guys? Yeah, they are. Why are they persisting like that? That's very strange. I might. That's very strange. Have they disappeared? Oh, they have disappeared. Okay. That's weird. Very weird. Never mind, they haven't disappeared. Give me 1 second, guys. Let me hold up. I'm gonna end stream. I'm gonna close this and then I'm gonna reopen on the same slide. Sorry, guys. I'm not sure why it was doing that. I'll start us right back to where we were. So let me start this and then let me, sorry, and let me stream again. Okay. Hopefully you guys can see that again, and then let me get my pen back. Cool. Very strange, my bad. So here this is Kb for our conjugate base. That's just that. We also have Kw, and so Kw is specifically for water. So we had Ka for acids, Kb for bases, Kw for water. So water has the ability to self-ionize. That's just something you need to know. This is the reaction. H2O can reversible into H plus and OH minus, right? The Kc expression for this reaction is called Kw. Since water is a solvent, we're going to write it like this. Kw is H plus and OH minus. Cool. At room temperature, the Kw for pure water, does Kw of water remain the same for any reaction that doesn't use water? Acid or base? Can you? Yes. That is. Oh. Actually, ask Panda that. Panda, if you're still there, if I'm doing a acid or base, if I have an acid or base in a different polar solvent, is that one still true? Surely if it's in a different polar solvent, that relationship between Ka and Kb is only relevant because they can convert into each other. He'll deal with that. Cool. Kw is this. In pure water is neutral in pH. An important characteristic is the concentration of H plus is concentrated to OH minus. If this is true, then the solution is neutral, right? If this is true, then it's pure water. There is no change in whatever. It is just equal to this. Remember, I did say that if temperature changes, the Kc values, so Kw, Ka, Kb, all of them, Kw, Kc, they will change with temperature. So at a different temperature, this value is different and this value is different. But as long as it's pure water, these two should always be equal. And if it's at room temperature, this is true too. Cool. So math magic. Just like hear me out. Ka was this. The conjugate base for Ka, or the conjugate base for CH3COH, was CH3COO minus, and the Kb expression for that was this. So this is Ka and Kb, Kw. If I do Ka times Kb, notice this term and this term cancel out, this term and this term cancel out, and all I'm left with is this times this, which is our Kw. So you can check this for every other acid and every other base. You can do it generically by just saying, yeah, I just said this. You can generically say, what if I had an acid that was HA and it dissociated into H plus and A minus? I'm not going to do that. I don't really care enough. But trust, for any acid and any base, that was the question you're referring to? Yeah, Panda will do that too. Ka times Kb is Kw. Cool. Another thing, we also have pH. So we had concentration of H plus, and we had pH, which hopefully you know that already. P stands for power. You don't. I guess you wouldn't know that bit. It's a logarithmic scale, so there's a log here. But we also have pKa, pKb, and pOH. So if they're ever at a P, all you need to know is just negative log of the same thing, right? Yeah, I guess you know pKw too. pKw would be negative, I guess negative log concentration of H plus times the concentration of OH minus. Sorry, it's kind of cut off. You can imagine it. Cool. They're all just negative log of what it actually represents. So yeah, what do you do with this? So what did I say? pH is the most common metric to measure acidity. So higher concentration of H plus, the lower the pH. I think you're pretty familiar with that. We can do the same thing with pOH. So higher the concentration of OH minus, the lower the pOH. Some other important things. In neutral water at room temperature, I told you that these two are equal. And at room temperature, this is true too. So pH is equal to pOH equals 7. If it's not room temperature, neutral water does not have a pH of 7. And in fact, all we know about it is neutral water for room temperature, concentration of H plus equals concentration of OH minus, thus pH equals pOH, right? If it is not room temperature, these are true, but pH equals 7 might not be true, right? A lot of people think, oh, well, pH equals 7 is always neutral, but that is only room temperature, right? pKa and pKb are relevant, but they're not relevant yet. I did have a question here. If anyone is interested, you can take a screenshot of that. I think I will skip past it. I was going to explain this one, but I think I might go past it just for time reasons. So take a screenshot if you haven't already. I'm about to show the answers. Those are the answers. Again, if you want to take a screenshot of that too, hopefully that, I don't know. Once we're done that, I'll give you a couple seconds. Cool. I'm moving on. The slides will be posted if you didn't get it. So, or you can ask someone in the chat. So, no. Indicators. Indicators, a special type of weak acid or base. Indicators in one form will display a color. So in this case, it's clear. And indicators in another form will display a different color. In this case, it's pink. Why are there benzene rings? Don't get ice. We'll get to that later too. There's a lot to cover. I will end up going over 2 hours, low-key. It's okay. Oh well. I'll try and speed run. This is a specific indicator. It's on your formula sheet. You don't need to know the structure or anything. I just showed this as an example. Here we have an acidic indicator, reacts with water. It becomes something pink, and it looks like that, right? So North Haley, yeah. Yeah, probably. Change color at different pH. So we're actually, you know what, we're literally about to get into that, so I will keep going. End time of the master class as of right now. Let's say 8:30. That is my guess. I don't know. That is my guess right now, 8:30. The next jump scare. This is an eye. These are eyes. My bad. I should have yeah, my bad for the jump scare. Um so we can have weak acid or weak base. HIN, this is some indicator, it is one color. It can dissociate in an equilibrium. What was the question? Well, pH of water is not 7 over temperature. I think basic. No. And Panda, if it helps, you can use this information on screen to explain that. I mean, this question kind of covers why it isn't, why the pH changes. Yes, I believe it is. I mean, I think this question is talking about that exactly. So yeah. So it can be acidic or basic. Same concept. It is one color in one form, and it can dissociate to be another color in another form, right? So the way it works, as I saw someone ask it, let's say I have this. If I add H plus, think about what will happen here, right? If I add H plus, then it will favor this reaction because it wants to get rid of this, right? I have too much of this. It wants to decrease it, so it's going to favor the reverse reaction. If it favors the reverse reaction, I'm going to get a bunch of this. And if I get a bunch of this, then it's going to look very strongly like color A. What if I take away? What if I reduce the concentration of H plus? Then it will try and create more of it. So it'll go this way, and then it'll create a lot of IN minus, and IN minus has a color, and it's color B. And so now it'll look strongly like color B. Same thing with base, where if I had H plus, it would react with this, and it would decrease this, and vice versa. So hopefully that makes sense. The point of this is that, if I roll this out, point of indicator is it will either have a lot of this or a lot of this, depending on how much of H plus we have. And that is with LCP. I didn't use the word LCP every time. But yeah. What do you do if the Ka or pH range exceeds of the solution? Ka or pH range of the indicator in the data book doesn't go that high. Yeah, just use the closest one. What happens to the equilibrium of an indicator at the equivalence point of a titration? I'm glad you are. Actually, we're not at titrations yet. We'll get to titrations. Yeah, I just had ping my alt account because I have my alt on the side. So, more indicator stuff. Just some basic questions. What is the Ka expression? I will work through these. So Ka equals concentration of H plus, concentration of IN minus, over the concentration of HIN. What is a pKa expression? Well, it is just the negative log of this stuff that I can't be bothered to write. So HIN and IN minus are different colors. The solution appears one color when I have more of HIN than I do IN minus. And it will appear another color when I have more IN minus than I have HIN, right? So the color change will flip over from one color to another when these two facts are equal, right? Do you notice anything special about pKa when the color changes? So if I write out pKa was negative log of concentration of H plus, concentration of IN minus, over the concentration of HIN. If IN minus equals HIN, then these two cancel each other out, right? These two cancel each other out, so they just disappear. So all I'm left with is the negative log of H plus, or the concentration of H plus. This, hopefully you've seen before, is exactly pH. So an indicator will change color when its pKa is the pH of the solution. He's proof by induction instead, if only. Hopefully that makes sense. That is a really important fact. The color change for any specific indicator, let's say I have some given indicator, the pKa, sorry, when the pKa equals the pH of solution, then the color will change. This is the color change point when they're equal, and we've seen pH equal pKa. Cool. So in your data book, this is just some basic stuff. In your data book, you have a bunch of different indicators, and you'll need to know when to choose them. You've got different indicators. You're given their pKa. You're given the color change range. What that means is, obviously, over time, this is an equilibrium, right? So if I had a bunch of this, then it will. If I had too much of this, it will turn into this, and it will shift slowly from having a lot of this to just a little bit of this to barely any of this to a lot of a little bit of this to a lot of this to a lot, right? That range is this. That is, you just have a range of values, right? And you can see the pKa is roughly in the middle of that range. Yeah. Um. Hopefully that is it. Cool. Titration. Um. Johannesburg, you're about to get another conflicting answer from me. um. Yeah. Anyway, titration. I was taught 10 to the negative. I'll double check, but I'm pretty sure I was taught 10 to negative 2. So pKa of the indicator tells us when HN, HIN. Yeah. I think I was taught 10 to negative 2, but and yes, very eloquent answer. Bigger. Yeah. I'm sure you probably done a titration prac in class, and it's hell. But anyway, you need to know these terms. Titrant is the solution that we're putting into the beaker. I'm sure you've seen a basic titration process, so I'm not going to explain it from scratch. Analyte is the thing with assessing. The indicator, in this case, it's pink, but like it's turning to pink, but it could be any indicator. And then, I don't know, we have the burette. I don't think the actual terms matter too much, but these are the main ones. Titrant, analyte, and we have an indicator. Question about phenol red, and it said comment about the relationship between pKa and the color change. He's right, plus minus 1. I need to see the question, but I think I know the one you're talking about, and I think Panda can answer that probably. There's some question where they use unknown they use unknown as titrant and known as analyte. Do we just do titration math the same way? You do, but that's a hella stupid titration because that defeats the entire point. But yeah. There's the question where you have to reference the burette and the flask to where a hygroscope. What? I don't know what that means. Anyway, titration process. It's called it's telling of volumetric analysis. We have some unknown base or unknown acid or base. Maybe we have some beaker. We have something in here. We're gonna slowly drop, bit by bit. I'll do like I don't know how to. I don't know. I'll just do a beaker pouring. Slowly, bit by bit, we're putting in something that's known that we know will neutralize this, right? So if this is an acid, but we don't know let's say we know this is CH3COH. Actually, that's a bad one. I want to use HCl, let's say. But I don't know the concentration. But I can pour in NaOH, and I can wait till this is neutralized. And once it's neutralized, I know that, oh, well, all of a sudden, once it's neutralized, I'll be able to, what's it called? Once it's neutralized, I'll know how much there was in here. So let's say there is 1 liter of HCl. I can just look at that. And let's say I add in maybe 10 moles of NaOH. Well, that means if 10 moles fully neutralize my HCl, then I must have started with 10 moles of HCl, right? And so if it's 10 moles in 1 liter, then the concentration will be 10 molars, right? Hopefully that makes sense. There is one problem. How do we know when it's neutralized? And figuring that out is kind of hard. We could just do it a super easy way, but no, we don't want to do that. That's not fun, right? We wanna have fun. And because we want to have fun, we're going to use indicators instead. And we will choose an indicator such that the pH equals the pKa, which we figured this out earlier, remember? We said that the color change of an indicator occurs when the pH is equal to the pK of the indicator equals the pH, right? So we choose the right indicator for the pH we want. So here is a strong acid, strong base titration. This is both ways. This is starting as an acid and we're adding a base. This is starting as a base and we're adding an acid, right? What do we know? This point here is the equivalence point. Equivalence point. It is when it's fully neutralized. That's all it is, right? For a strong acid, strong base titration, it should always be at a pH of 7, right? This is our endpoint. Endpoint. It is the end of the titration, right? Hopefully that makes sense. And the pH for this, again, we're assuming at room temperature, right? If it's at room temperature, the pH for a strong acid, strong base titration will be 7. That's it, right? What if I had a weak acid instead of a strong acid? Well, let's do this bit by bit. I guess the process is still the same. We can still neutralize it, right? Full balanced equation. Here we have CH3COOH reacting with NaOH. AOH. It is a neutralization reaction, so it is not reversible. So one way, CH3COONA plus some water. If I perfectly neutralize my analyte, at this point, what species are present in the beaker solution? Well, if I perfectly neutralize, I have nothing here, so I'm just working with these guys. So what's present is I'll have ethanoate ions, sodium ions, and water. Endpoint in the position you put in the glass should not be where the indicator changes color. The equivalence point is where the indicator changes color. The end point is just the end. The equivalence point is where it changes color. That's really important. Endpoint is different. You need to know both terms. That's why I annotated it. What's the endpoint useful for? Nothing. Literally nothing. Am I? Wait. I mean, I'm pretty sure I'm not Johannesburg. Yeah, that's what I said. Isn't it? Have I mixed up the words? My bad, guys. My bad. Somewhere there? My bad. Hopefully that's fine. Wait. It should just be somewhere on the steep part, right? My bad. Cool. Is that okay? Am I good to move on? My bad, guys. Okay. Do you know 141 tomorrow? Not gonna lie, I've forgotten. So yeah, these are the things present in solution. Answer question above. Are there any strong acids or bases present? Well, we know ethanoic acid is a weak acid. So that tells us that CH3CO minus should be a strong base. Yep. I think it was on the slide, I didn't say it exactly. Strong base just means it's a relative term. So it's stronger than the ethanoic acid was, right? Cool. And then moles neutralize each other. Yeah, it does matter. Stoichiometric ratios do matter. Yeah. Cool. These are just the answers, same thing. So let's actually look at yeah, it is forward arrow only, by the way. Just want to point that out. Let's actually look at a graph before we continue, right? So here we have the I don't know, equivalence point, but our graph looks a little bit different. Here we have this weird wobbly zone, right? And what this bit is our buffer zone, buffer region. I'm not sure if it matters. I'll call it buffer region. Remember when we were talking about buffers, and I said that there are two ways to make it. One way was, I guess I didn't really cover it too much, but one of the ways I did mention is we start with some amount of a weak acid or base, and I half neutralize it, right? That's what's happening here. So if this was like, I don't know, 28, then at 14, for example, it's half neutralized, right? I don't know. And my point is that this is a buffer region and it resists a change in pH. Polyproduct titration calculation. I don't have one like here, but I can find one later, or if someone else has one, you can send it in the chat. So this is buffer region. It will resist a change in pH. That's why you can see that it starts decreasing really slowly. For an increase in volume, it only partially changes the pH. It is a very small amount. That is the buffer region, right? Aside from that, everything else is the same. And remember, we said stuff about bases. Okay, yeah. And for this, notice that this point here, or the equivalence point and stuff, it is higher up. Earlier it was at 7, right? We found that for a strong base, strong acid, it was at 7. But now the equivalence point is slightly higher up, so we'd probably want to choose a different indicator. For this one, I'd probably be inclined to use like phenolphthalein or something. But you can look at your formula book; you have all the list there, right? But the fact that it's above 7 is really peculiar, and we want to figure out why. So let's see. Firstly, we remember that of the species that were present, CH3COO minus was one of them, right? Yeah, it's going to go on for a while. I'm going to try and speed run the second topic. I had a break in the middle. We're going to have to skip it. Anyway, CH3COO minus was one of the species present, and it's also strong, right? That is quite important. It's a strong base. And what do strong bases do? They want to react with water. So this strong base will undergo plus H2O, and it will go like this, CH3COOH plus OH minus. It'll do this, right? It'll only do it by a little bit, but it will do it, and that's kind of important. And what will happen is, because I just had this, it will react with water, it will form this, it'll produce some of this and some of this, right? If I produce OH minus, then I know that the concentration of H plus times the concentration of OH minus equals 10 to the negative 14, because this is Kw equals 10 to the negative 14, right? Well, if I know I'm producing some OH minus, let's say if I increase concentration of, actually, it's probably easier this way. Here, let's do this instead. pH plus POH. If you told me to on another day, nah, I'll finish it. It's probably a bit of a pain to do it over multiple days. If I have something like this, if the concentration of OH minus, if concentration of... No, sorry. I want to go back to what I had earlier. That's my bad. H plus OH minus equals 10 to the negative 14. If the concentration of OH minus increases, then the concentration of H plus will decrease. Therefore, pH, because pH is negative log concentration of H plus, so therefore pH should increase. Right? It's a very crude way to say that if, because of I am doing a weak acid, this is a strong base, and the strong base, through a long series of events, will cause the pH to increase. That's why this equivalence point is higher than 7. It looks like this on a graph. The equivalence point is above 7, which is what it should normally be. There's a lot more make my... What? But yeah. Cool. And then this is the same thing written out in full. I'm not going to annotate this one, but weak base, strong acid, similar stuff, right? Base is pH 7, so it dominates pH. Base of pH 7, so it dominates pH for solution if it's strong. Yeah. I did this is a very crude drawing. But yeah. Because of this changes. Cool. I'm not going to annotate this one. It's the exact same thing. We have a weak base, starts up here. We had a strong acid, it'll end up down here. Again, buffer region, same thing. Off the top of my head, I think I remember seeing that question, and I think the starting point didn't matter. It just had to be approximately right for a strong acid or a strong base or whatever it was, but I'm not 100%. So yeah, weak base, same stuff. Buffer region, same thing. Equivalence point is slightly below. The reason being that here we had a strong base. For this case, we'll end up getting a conjugate as a strong acid. And the strong acid will push the pH down from 7. The equivalence point will be lower. Cool. Finally, we're almost at the end of topic 1. It has gone on for a while. Rice tables or ice tables. I've heard both. I've learned it as rice tables. It's just the same thing. This one you don't need to use. This question you don't need to use as an ice or rice table, but I'm going to anyway because it's a really nice example. So acetate ions have a Kb of around this value here. I have a 1 molar solution of ethanoic acid. What is the pH of the solution? So let's start with this. Here, I know my initial concentration of ethanoic acid is 1 molar, right? That is what I started off with. But 1 molar, but it's not going to stay as that because some of this will turn into this, and that's important. So maybe we start off with like this. This is our initial, right? We write all our initial concentrations for all of our different values. Right, so question, never enough room for working. Yeah, I know. Then we write the change. So all the changes should match the either a plus or minus by some amount. So here we know we're going to favor the forward reaction because I have more of this than I do this, and I want to favor the forward. So I'm going to lose some of this. I don't know how much. Let's say some, right? I'm going to gain some of this, and I'm going to gain some of this, right? So my end concentration should be, at equilibrium, these should both be x. This should be 1 minus x. Then, this is an important fact. QCAA says quadratics are too hard for you guys. And so you're not expected to have to solve anything like that. No. Quadratics are literally just that. Quadratics are too hard. So they will simplify it, and this is how they simplify it. Teacher will teach different things. I saw 10 to the negative 4, 10 to the negative 3, 10, and I've learned 10 to the negative 2. But if the equilibrium constant is having the marking guide, they can have like something asking you to square root, but they should never ask you to use the quadratic formula. That should be out of syllabus. Yeah. This is okay, but solving a quadratic with a quadratic formula is too hard. Yeah. In the case that the equilibrium constant is small enough, I learned if it's smaller than 10 to the negative 2. I've heard 10 to the negative 3, 10 to the negative 4. I don't know. It teaches you different things. But if it's small enough, we can say that the reactant concentration doesn't change. It is approximately 1. Is huge. I don't know. So yeah, it approximately doesn't change. And so from there, I'm not gonna I guess have the rest of the answers here. This is the rice table. This is the main bit, and then we can do some maths. We need the Ka value, and we know Ka times Kb is Kw. I stated this earlier. So we can solve for Ka by rearranging, and we get this value here. We know that the Ka expression looks like this for our equation. It's equal to, we have our equilibrium values here. This is 1. So x squared on 1 is x squared. And then we just equate them. So our x squared from here is equal to our Ka from over here. And then we get our value for the concentration of H plus, which is x. Which applies to the titration question. Yes and no. There is a question with this in titration, but I've left it as an exercise for you guys because I don't know. What I'll do is I will send it, I'll show you the question, and then I will send the solution in the chemistry help channel later. That'll help. That's the exercise to the reader, yeah. So concentration H plus is this, and then pH is the negative log. Don't care, 1 minus x equals 1 in most cases, yeah. Because the Kc is small enough, that is why. Kc is small enough. Cool. This was going to be another question. I'm just going to skip it. You can take a screenshot if you want it. I'm not going to cover it. I'll give you a couple seconds to take a screenshot. Cool. This is the question I was talking about with titration. This is probably the hardest topic, or hardest question you could get for Unit 3, Topic 1. It is hard. It looks so deceptively easy, but it's hard. Feel free to take a screenshot. I will post this in the chemistry help channel maybe later, and I will send a solution in that as well. Rice table on every pass paper? Probably. I want to give you some time to try it. I'm just worried about finishing on time. I will explain how to do it. I just don't think I have time to do it right now. I'm going to post it later, and I will post my full solutions. Explains for strong acid, weak base, why changing the concentration doesn't change pH and equivalence point. Strong acid, weak base, why changing the concentration doesn't change pH equivalent. I'm not sure I understand your question. We will finish. You know what? Okay, I'm gonna push this. I'm gonna say we're gonna finish at 9. So we'll finish at 9, and I'll give you guys a couple minutes to. This is gonna be a break, anyway. This will be a break. Looks like Panda got that one. And so Unit 4. I'm not doing Unit 4. Unit 4 is for someone else. I'm just doing Unit 3. This is the end of Topic 1, though. So I can join it. Yep. So I'll give you guys the question back. Yeah. If you guys want to take a break, we'll take a short while. We'll go to like 8, maybe 8 or something. I don't know. And then I will continue with Topic 2. There's your question if you want to try it. It is quite difficult. It looks easy, but it's not, I swear. To the recording if you don't put it up. I am not the one. Question above. I don't have slide on right now. Where was it? Wait, can you reply? For some. Oh, there we go. See me up. Mark allocation. Sometimes they range from 3 to 4 marks on past EAs. Wait, you say for these type of questions. I don't know what the type of questions you're talking about are. Oh, no? It was about LCP. Um, when this is finished. This question, for if you're talking about the one I have on screen, this question is definitely more than 5 marks. Definitely more than 5 marks. Oh, about LCP. Okay, okay. Basic ice. Okay, okay. I have a very crudely written solution that I can put in. Let me see if I can find it. Um, if I can find it, I will send my very crude solution to this question. Do you know what they want for every mark? No. No. Um, there's just not, unfortunately. Let me find the solutions I had written a while back. Okay, never mind, I can't find it. Where is this going to be uploaded? Um, I believe it's to, like, actually, I don't know. One of the mods can answer that. I am not 100% myself. Mods, someone answer. Um, LCP visible effect. The marks will just be something like, what is the change? Whenever I'll get the marks will just be like, what is the change? Let's think. What is the change? What is the effect of that change? So does it change like pressure, concentration, etc.? Um, mention LCP somewhere. I don't know if these are okay. I don't know what the marks will be, but these are the things you should do. So mention the change, or what is the effect? What is the sorry? What is the change? What is the effect of that change? Mention LCP. Explain which reaction will be favored, forward or reverse, and why. Say what is the result of that reaction being favored. So maybe it will re-increase something, it'll change the temperature back, or whatever. If there's a color change, so I think in this question there is a color change. I think that's from a neat paper. Um, created there on the chemistry channel. I don't know what that was about for all. And you would just say the color change as well. That would result from that. Let me. Here, what I'll do. Yeah, this question's a hard question. I will send. I'll take a screenshot of this, and then I'll make a post in the chemistry help channel. Wait, did someone else do it? Oh no. Okay, never mind. Why is it not letting me type? There we go. Chem question from master class. And then let me copy my solution. I posted my solution there. No spoiler. No cheating. Help channel solution for easy to access. Um, I mean, like, I can pin the solution in the channel. Um, So yeah. Okay. That is probably enough time. I will probably have to keep going. We will probably end up going till like 9, but it's okay. Um, that is the end of your break. I apologize. Um, what was your answer? Okay, the 1 point. I don't remember. If that was the answer, then yes, I am very proud of you.